Hello and welcome to Team 74's presentation. My name is Devesh and joining me are Ian, Zach, and Joey, and we will be presenting our findings regarding our prototype gears. Today we will discuss the team's general design philosophy and factors during the creation of the final model, as well as the results and possible improvements that we considered. Before getting into the logistics of the robot, the needed background must be established. Every year across the globe, disasters strike, incapacitating communities from receiving basic resources and care. These problematic scenarios arise from both natural phenomena as well as human conflict. In both cases, people are dislocated, infrastructure is torn down, and communities are generally thrown into chaos. To recover from such events, outside sources aid to ensure basic necessities are met. However, many times there is no clear path in delivering materials, so the team was tasked with the following mission: creating an autonomous robot that would be able to deliver the needed materials through rough and treacherous terrain to affected communities. As this assignment includes a good deal of concepts and constraints, a set of objectives were placed to aid the team in designing a proper and efficient model. An importance was placed on four major areas of the design process: the precision while navigating through rough terrain, the identification of potential hazards, the release and containment of deliverables, and finally the ability to effectively communicate the contents of the given cargo. To begin management, we made it a goal to complete the given objectives. To start off brainstorming possible ideas, the team took inspiration from prior sources such as aerial and ground vehicles. It became quite obvious that the latter was more possible, and the team began researching vehicles that responded well to terrain, and using rather large wheels became a recurring theme. There was also a bit of research done about what would happen in the case where the robot was put under too much stress or got caught in a certain space, but after more review, we chose not to place emphasis on it given the constraints and possibilities of the mock disaster test. Here's our FBD with multiple inputs and outputs as seen on the right. We also created a work breakdown structure that dived a bit deeper into each one of the needed components and is seen on the screen. As we continued brainstorming, the team ended up separating the robot into two physical components: the driving mechanism and the cargo offloading mechanism. During this period, there was much thought put into the amount of wheels and the proper turning mechanism for the drivetrain. For the offloading portion of the robot, there were a couple ideas regarding a motorized ramp, and even more that simply implemented a chute that released the cargo to the needed location. As we had all these requirements, a needs-finding table was created as seen on the following slides. Finally, to finish off the project management, a Gantt chart was established with time periods in order to keep the total production on time.
The team was tasked to make 4 symbols to represent what was encased within the cargo container. Initially, this task seemed simple until the fact that these symbols must be understood and not offend any potential cultures or groups of people that they are presented to. The symbols must be able to represent emergency shelter, food and water, medical supplies, and fuel. These symbols should be original. For example, the Red Cross is already a universal symbol for medical aid, so it could not be used. Firstly, the team started by brainstorming ideas by using the method of rapid ideation by firing out any ideas that came to mind. Quickly, we came up with the list shown. We would go on to do research to decide which symbol would be best understood throughout all cultures. For example, when researching the food symbol, we found that there is a strong correlation between the production or growth of a crop and the likelihood of finding it in the food there. So we looked at the production maps of these foods and found that a lot of the maps were grown in multiple continents, but rice was an outstanding crop as it was grown in more countries than the rest of the foods. Additionally, many countries that rice is not commonly grown in still know what rice is and may even have it in their common dishes. We followed a similar process with the other symbols as we looked at multiple countries as symbols for these demarcations. While emergency shelter and medical supplies were already deemed universally understood by the team through research, the decision for fuel symbol was not as easy. Because fuel must encompass more than just gasoline, we decided to put more to the symbol. However, we figured that if someone was in need of oil or coal and saw the symbols of fire or gasoline, they would likely still open the cargo. With these symbols, we sent a survey to many Purdue students with all diverse backgrounds and a diverse pool of cultures. We asked what these symbols represent, and the students would give their response via typing. With 53 responses, here are the results. Just under 4% of people found the fuel symbol offensive, while all others were deemed completely non-offensive. 90.6% of the people could correctly decipher the emergency shelter symbol, 81.1% of people for the food and water, 100% for the medical supplies, and 88.6% for fuel.
When creating initial ideas for the gears, major needs for the physical design had to be created. These needs were that the gears had to be stable enough to support the cargo, can turn and navigate within the confines of the maze, meaning it needs to be small and needs to be able to turn within a small turn radius. It needs to have enough room on the gears to place the cargo and other various electronic parts such as sensors, and it needs to appear friendly. 3 prototypes were created and tested in order to determine the best option. The first prototype was a large rectangular base with 4 wheels and 2 motors powering it. The wide base allowed for good support of the cargo and other attachments that were needed. However, it was found that the prototype struggled with making tight turns and was projected to be too large for the maze. The next prototype aimed at solving the turning problem by removing the back 2 wheels and implementing a peg leg or simple Lego piece that would support the weight of the gears. This design, while able to turn with a tighter turn radius than the prototype 1, struggled with being stable enough for the cargo. The third prototype replaced the peg leg with a single rear wheel that can freely spin as the gears turned. This design proved to have the best turn radius out of all of the previous prototypes and improved the stability of the gears. However, it lacked room underneath the gears, which was needed for the cargo delivery system. In order to find which prototype seemed the most friendly, a survey sent out to the general public provided results that said the majority of people preferred the smaller form of prototype 2 and 3, rather than the large rectangular base of prototype 1. A subsequent question also asked what additions would make the gear seem more friendly, and the most common response was that the inclusion of a face would make people most comfortable. So in the final design, a large smiley face was included. Following testing, a decision matrix was created, highlighting the different needs of the gears, and after completion, it was clear that the third prototype was the most effective design and would be utilized for further testing and development. The first cargo drop-off system was to be mounted to the underside of the gears and would consist of a table that would slide in, causing the cargo container to fall off onto the ground. This design had a large flaw in that the cargo container was simply too large to fit on the table, leading to a necessary redesign. The new design consisted of a system implemented on the rear of the gears, where the cargo would sit on top of a trapdoor and fall to the ground. This design was very reliable, however ended up causing the gears to be too large to make effective turns within the maze.
Now moving on to the software design philosophy. To start off, I'm going to go over the purpose of the sensors and the motors. Like we said earlier, the gears had ultrasonic, infrared, and IMU sensors. The ultrasonic sensors were used to detect the distance in front, to the right of, and to the left of the gears. The infrared was used to detect infrared hotspots in the close proximity of the gears in the maze. And finally, the IMU was used to measure angular velocity as well as detect magnetic fields in the maze. For the motors, the front 2, as seen in the picture, were used to drive the gears, and we also had an undercarriage motor not seen in the picture that was used to release the cargo in the back. Now moving on to the turning code. Our gears used 3 types of turns: right, left, and a full 180, which is just turning around. So, as far as logic goes, we have a flowchart on the right. Basically, our gears would rotate the front 2 motors so that it would either turn right or turn left, and the full 180 would also do a right turn, but the angle would just be different. So as you can see by the diamond shape in our flowchart, it says, is the angle greater than 90 degrees? So if it had reached over 90 degrees, it stopped turning, which means that it would do a perfect 90-degree turn to the right or to the left, depending on which function we were doing. And if it was doing the turnaround, that 90 would be 180 instead. So in order to do this, we use the IMU to track angular velocity, and that angular velocity was integrated with respect to time, so we would know how many degrees it had turned in a certain amount of time. And that's when we stopped it at 90 or 180, depending on the type of turn. Now moving on to distance determination code. Like I said earlier, our ultrasonic sensors detected the forward, left, and right distances from the gears. And we also found that the gears was 22 centimeters wide, and we found that the corridors were 40 centimeters wide. So we had 18 centimeters of space to work with. So in order to keep the gears in the middle of the corridor, it would need 9 centimeters on the left and the right of itself. So in order to preserve that, we had feedback control in our forward movement code. So using the measured distances, the gears was able to utilize proportional, integral, and derivative feedback to control the front 2 motors. So the right, like if the gears got too close to the right wall, the ultrasonic sensor on the right would see that that distance is less than 9 centimeters, so it would speed up the right motor in order to try to get itself back in the middle of the corridor. So if the gears was actually centered, the motor speed would be constant for both the left and right motor. Now moving on to traversing the maze. The main code contained every possible scenario that the gears could have run into in the maze. So a couple examples would be if there's nothing in the front, nothing in the right, nothing on the left, it would default to left. But if there was a wall in front and to the left, it would turn right because that is its only option. So as you can see in this video, we have that example. I'm going to start it now. So it doesn't see anything in front of it, doesn't see anything to the right, but it sees a left. So it turns right, and then it starts utilizing the feedback control as it is moving forwards. So you can see that it's attempting to stay right in the middle of the corridor. While it was doing this, it also searched for magnetic and infrared hotspots using the infrared sensor and the IMU. And if anything was detected, the gears would immediately turn around and head the other direction. Anytime the gears detected an infrared or magnetic hotspot, it would also add information to the hazard identification text file. So the information that was added would be the type of hazard, the magnitude of the hazard parameter, as well as the location of the hazard on our map. This text file would be immediately accessible after the conclusion of the gears voyage.
To successfully map any hallway that the gears came across, a program was implemented that could add the full length of a hallway when finding it at an intersection. To do this, several important data points had to be kept track of, including the direction of the gears is facing, as well as the current location within a coordinate system that the gears is at upon reaching an intersection. Using this information, a while loop created the line of ones to extend the length of the hallways in the 10 by 10 array using NumPy. This matrix was then outputted at the end to show the completed map. The current location function was vital for the gears to successfully create an array within the map of the maze. This function utilized the information on the initial length of the hallway it turned down that was found prior, and then uses the remaining distance of the hallway to determine where in the hallways the gear is. Using this, the direction the gears is facing, as well as the previous known location, the program can successfully determine the new current location within the maze.
One positive aspect of our design was the cargo drop-off. Through testing, we found that the drop-off was effective and consistent, as it always dropped off the cargo upright. As seen in the video, this is how the cargo was dropped off. Additionally, the gears is able to navigate the maze with relative confidence as seen in this video. Although the navigation was not perfect or consistent, we considered it a positive aspect within the design. Next, the program was easy to implement and understand, so if another person or group were to improve the gears in the future, the process would run smoothly. Lastly, the turning radius or potential turning radius was small. However, one of the negative aspects of the gears design negated that. The size of the gears design, in particular the length, prohibited the gears from properly making 180-degree turns and sometimes 90-degree turns. Unrelated to its size, the programming implemented struggled to consistently have the gears turn as well. Additionally, mapping and hazard detection were not consistent, as sometimes the gears would not map the last hallway it went through, or a random hazard would be detected. In conclusion, the gears was neither a success nor a complete failure. In theory, gears should have been able to do all things it was asked, but more time and testing would be needed to perfect its software, as well as modifications to its hardware and size. This factor would be especially important when thinking about scaling up the gears. Because all features were already present within the gears design, we are confident that the design could be improved greatly in the future. Thank you.